Grazie Andrea, grazie a tutti, buongiorno. Buongiorno a tutte e tutti. Vorrei ringraziare innanzitutto la Commissione organizzatrice di questo convegno per l'invito. La frase "io non rischio" contiene tutta la filosofia di ReLUIS, così anch'io, per non rischiare, e con il vostro permesso vorrei girare la presentazione in inglese. The topic will be hybrid simulation in support of earthquake engineering. And please don't go away, those who don't know about hybrid simulation. I will explain briefly very soon. So we will go a little bit through an overview of the hybrid simulation method and its contribution in earthquake engineering. And principally, I will be showing some applications only, not hard stuff. And finally, some assessment of the method. So what do we need to test? Actually, we all know that the seismic response of civil engineering structures is highly nonlinear and inherently nonlinear. So full-scale testing is necessary, and it's necessary because we have to deal with large structures, massive structures. We need to verify standards for the design of new structures. We need to assess existing structures and actually study also how to increase the capacity through retrofitting techniques. We introduce new materials in construction, and thus we have to test them before being applied in practice. And we need to verify seismic devices in full scale before the application. So the need for experimental testing exists, and it's very intense. And this is very obvious also if one looks how our ability to predict experimental results, how does it fit. And in certain cases, in blind test predictions like this one on a four-story structure in e-defense shaking table in Japan. And you can see with a red line depicting the measured response, and the other curves depict the prediction of several groups. Of course, there's always a group which is competent enough to match pretty well the experimental results, but the deviation that we see among the predictions is notable and also worrying sometimes. And what tools do we have at hand? We have, in the experimental methods, we can go from the slow static testing to dynamic testing if one sees the rate at which we test the structure. In between lies the hybrid simulation. And if we see how if we count the response realism of each of these methods, the cyclic testing at low cost can have little realism with an actual seismic event, the response of a structure in a seismic event. On the other hand, shaking table testing is the real thing, but even done at scale. But this comes at high cost. The hybrid simulation strives to lie in between, trying to have a good enough prediction of the response of the structure, but at a reasonable cost. And of course, hybrid means that we merge two things. And what do we strive to merge? We strive to merge our numerical capabilities for things we know to experimental testing for the things of a structure, for the parts of a structure that we don't know really well. So the main idea is that we split the inertia and damping forces which are accommodated by a numerical model for the part of the structure or the whole structure or the part of the structure that we really know the response. We can describe the response pretty accurately. And then regarding the seismic resistance of specific parts of the structure, we rely on the physical modeling. So actually we can construct a specimen in the lab as in the picture, and then running a code and solving the equations of motion, getting the displacement for each step of the accelerogram, feed that displacement to the actuators on the structure, measure the force that the actuators need to apply these displacements, and then feed back this force, which is actually the product of the stiffness times the displacement. But it's the real thing. We don't make any assumption on that. And this becomes the initial point for starting for the solution for the next time step. So it's a step-by-step procedure. And just a brief historical note, initially this technique was termed online computer control test or pseudo-dynamic test. also the word pseudo is not very, it might be misleading sometimes. It's not the real thing. Everything happened at the University of Tokyo initially in 1969, so it's already quite some decades ago. And they ran several tests until the 75. Actually, in 1975, they conducted the first substructural test. I will go through this in a while. Then the hybrid simulation, also dynamic technique, its evolution can be distinguished in decades. So between 70s and 80s, there were many tests at the University of Tokyo, both on concrete frames and steel structures. Then the US-Japan joint research project gave a large impetus to this technique, so it started being applied also in the United States at several facilities, like the one at San Diego, between the 80s and the 90s. And from the 1990 and 90 until today, the method initially saw a great development thanks to the NIS NSF project, which was a 10-year project of $80 million that really paved the way and created many, many tools that we use even today. And it was then that the term hybrid simulation was coined for this technique. Just to note that since 2000 till today, there are more than 200 papers, and maybe I haven't counted them pretty well, on employing this technique. To implement this technique, we need certain ingredients. We need hardware, but not something special. Normal hardware with some characteristics. We also need special software, though, because we are coupling two entities, the numerical part and the experimental part. And there are several platforms available, open source platforms available for this scope. Normal control schemes can be applied for the dynamic testing technique, but also newer ones can be employed in certain cases, like mixed control, force and displacement, or switched control, switch during the test from force to displacement if you go over the tip, the peak of the force. You need communication among the components because you have to communicate, your controller in the lab has to communicate with some numerical solver. And for all this, of course, we need quality and reliability. And the reliability depends on the errors that appear, both on the numerical part and the experimental part. I won't go through the details. It's not the place, it's not the time to do so. But I want to stress that there are experimental errors, and the problem is that if we don't take care of these errors, they accumulate because this technique is stepwise. So we run through 2,000 points of an accelerogram, and if you have even a tiny error in the force or the displacement in which you apply to the structure, this accumulates because the new values that we measure bear this error too, the influence of this error too, and this accumulates through the test. So I will skip this. There are several error tracking indicators. They have been developed both for the local response and the global response. And principally what we might want to look during the test online, a good indicator is the energy indicator, input and consumed energy during the test. This is a good indication if the control is good and the test goes well, because there is no other way to understand if the structure deviates due to experimental errors during the response. And the hybrid simulation technique comes in several forms, so there is a lot of flexibility depending on the problem we want to study. And this is very important. You can run a normal pseudo-dynamic test very slowly to take 3 or 4 hours, but you can run a real-time hybrid simulation test, which runs in approximately the same time scale as an actual earthquake, so like a shaking table test. But we don't have a shaking table. The structure is fixed at the floor of the laboratory. So this is all I want to say about the method at this point. And I would like first more to stress on the applications. So we will go through some full-scale tests that have been run with hybrid simulation technique. Some hybrid simulation tests, including with substructuring, continuous hybrid simulation with substructuring, tests on non-structural components, about solid structure interaction, and distributed hybrid simulation. So one of the first tests we conducted in our laboratory was a two-story structure. And this structure contained all the structural deficiencies of existing structures. Small dimensions, lack of stirrups, deficient lap splicing, and moreover, one side of the structure was had a higher stiffness, a double stiffness than the other side. So the columns on one side were 25 centimeters, on the other side they were half a meter. So this was provoking, obviously, a torsional response of the structure. And how does such a deficient structure respond to this structural characteristic? So this was important to run. And this test was in full scale. There's no substructure. And a numerical model was producing the displacements and the rotations that we needed to apply at each floor. And with 2 actuators per floor, we could apply displacement and rotation as prescribed by the numerical simulation. And this technique was applied in 2 configurations of the structure, one a regular one and one with an open story. So the upper story, you see in the picture here, the upper story is infilled. Of course, we don't do the test just to identify the deficiencies, we have to correct them. And then we can employ several techniques. And in this structure, we employed a series of different techniques. In the first case, we attempted to reinstall the stiffness balance. So we jacketed the columns on one side. So we had the same stiffness on the 2 sides to take off the influence of the torsional response. In another case, we provided sufficient ductility to suppress any brittle mode of failure. So all the joints and the upper parts of the columns were wrapped with 2 layers of fiber polymers. And also the same case applying textile reinforced mortars. Another test that we performed in full scale regards a steel structure, and this is actually a collaboration with a team led by Professor Di Sarno and in Project IRIS. And in this case, again, there is a difference in the stiffness on the base of the columns of one side with respect to the columns on the other side. And this provokes, obviously, the torsional response. But on top of that, we needed to apply 2 seismic motions in 2 transverse directions. And this has been done in the lab. And another thing that we wanted to observe also what is the effect of having successive seismic motions of such structures. So if we have a repetition of seismic input one after the other. And also this requires some adjustments in the testing strategy because the numerical solution provides you the displacements at the center of stiffness of the structure in the global coordinate system, but then when you command the actuator to apply a displacement or measure a force, this is done along the axis of the actuator, which does not coincide with the, does not coincide with the center of the global reference system. So we need transformations, geometric transformations between the commands sent to the actuators and then from the measurements we take from the actuators to feed back to the numerical simulation. I have a short video on that in which you can see the response of the structure, and this is a graphic of the response to the 2 seismic motions applied in transverse directions and what the 2 different types of base connections do during, excuse me, what have I done? Okay. So on the upper left, you can notice the movement and the torsional response of the structure, the biaxial response, and also what is happening at the 2 types of at the 2 bases of the structure. This is a distinct advantage of the hybrid simulations in the hybrid simulation because it's running slowly. You can stop the test, you can restart the test. You cannot do that in a shaking table. You can observe things in between. You can mark the cracks. You can have information at any stage you want. But then, according to my opinion, the strongest characteristic of a hybrid simulation is the possibility of performing substructuring. Substructuring means that in the lab we bring only the part of the structure that we want to study, and the rest of the structure is another substructure which we can model adequately well, and it's running in a numerical simulation. So in the lab, you don't need to construct a whole bridge. You just place the isolator in the lab, and the deck and the rest is in numerical simulation. So in a simulator. So in this case, for example, if we consider the technique of bay infilling, that is the technique that we increase the stiffness in certain bays of the structure so that displacements decrease for the other members of the structure. This is a technique often used because we only employ interventions on the external skirt of the structure. We don't create problems to the inhabitants of the buildings except to some special points, and then we just infill with concrete all the base of the structure on the height, and obviously we have to reinforce also the foundation because the moments are increasing. So for the whole structure in the lab, one can find only the 4-story shear wall that becomes after the infilling of the base, and it's laid horizontally because the height of the lab does not permit to have 12 meters of height of specimen, 9 meters in this case, sorry, in the lab. So this is horizontally placed with supports below and swivels that can take up the own load, the self-weight of the wall. And in this case, the topic of the study was how to obtain a monolithicity between the initial frame and the reinforced concrete that we placed inside the infills, and what are the measures, how many dowels, and how close to each other should we place that we guarantee such a monolithicity. And the second issue that we studied this was an experimental one, is that for stiff structures, there are certain difficulties to apply the high-bay simulation because being very stiff produce very tiny displacements, and these displacements may create control errors, where displacements, we are talking about displacements of the order of microns. Imagine you have a rock and you have two actuators. The actuators never stand still. Even the slightest movement, 1 or 2 microns of one actuator, because the structure is stiff and the actuators are anchored on this block, they are being felt by the other actuator, which needs to compensate and place the specimen in 0 position again. So the actuators start fighting between each other, and within seconds you find some hundreds of kilonewtons being applied to a structure at very small displacements. So this cross-coupling, this tight cross-coupling can be faced with different techniques, but may lead to instability if we don't take care of that. And also this, in such a case of a very large structure, we try to take advantage as much as possible of that. So we had this idea that we employ a very heavy reinforcing technique on 2 of the sides of each bay. So we follow the prescriptions of the codes of how many dowels we need to place to take up the shear and how many other dowels we place to connect them with the reinforcement that we will place within this bay each time. So you notice that there's much denser reinforcement in one case and much more sparse apart in the other case. So 2 of the sides were reinforced with one technique, 2 of the other sides of each floor was reinforced with another technique. So with one specimen, you can study 2 different types of interventions regarding the response. Also, there are other cases which really stress the importance of substructuring. In high-rise buildings or multi-story structures, many times we have shear walls which are coupled. So there is a link beam, a coupling beam between the walls, because this is better for their response. And if we want to run a test on the behavior of such links, it's very difficult to do it in full scale. Why do we need to do such a test? Because when these beams become nonlinear, they expand in length, and then the walls try to prevent this expansion. So there is an increase or decrease of the axial force on the beam, which we cannot really calculate or we cannot know beforehand to run a small, just a cyclic test with just the beam. So in this case, it's an 8-story structure. For all the beams above the 1st story, we employ the finite element model, and for only the coupling beam of the 1st story, we represented it in the lab. This is turned 90 degrees. So imagine that this is the coupling beam, this is the wall, and this is the other wall. So in that case, we can apply and control the forces and displacements in the degrees of freedom of this coupling beam, and we take the results which arrive from the simulation. But it's not only for buildings, this technique. We can study industrial buildings in the sense that there is other equipment like piping that crosses structures, and maybe when these two structures with different characteristics are excited seismically, then we need to know how to, what is the displacement history that we need to apply to such a piping system to check its integrity. And then in this case, because this displacement history is unknown, the only way to do that is to have the numerical simulation of the two buildings and then apply the displacements which result for the piping system in the lab. This is a 14-meter long piping system, and we can employ also advanced techniques to, of course, watch closely the most vulnerable parts, like the elbows of this piping system. And regarding substructuring, there's another also example like this bridge, this multi-span bridge with simply supported beams, in which we wanted to see the behavior of the elastomeric bearings. And elastomeric bearings are not rate sensitive, are not very rate sensitive in the sense that the velocity of movement is not affecting very much their properties, but still this is nothing we have to take care of. And in this case, we employed a correction technique in which we corrected the force that was coming out of the actuator to take advantage of this missing part that the test was run slowly instead of being at the rate of an earthquake signal. And here's an example of how we split the matrices between the numerical part, the physical part, and the degrees of freedom in between. But it's a way to increase the testing speed before, of course, arriving at real-time testing. And another really very attractive but difficult characteristic of substructuring is that you don't need to have the numerical and the experimental parts in the same place, in the same lab. You can have the numerical part anywhere in the world, and you can receive in the lab the command displacements from a numerical solution. This is very important in cases that someone has built a model somewhere in the world that, of course, we cannot ask for the code. And what we can do is just give him the opportunity to send us results from his code, and we apply the forces in the lab. So there is a synergy there that is really very, that's enhancing the potential of hybrid simulation. In this case, the hybrid simulation regarded a three-span bridge, an actual bridge in Greece, for which the piers, the intermediate piers, and the deck, and one of the bearings at the end were numerically simulated, while the bearing on the other end was tested physically in the lab at the University of Patras. So there was part of the numerical simulation was done in Canada. Other parts were done in France, in Greece, in Thessaloniki, and in the United States. So all these numerical tools were communicating to the lab through the internet the values of the displacement we need to apply. We restituted back the force we measured. And also the hybrid simulation can deal with solid structure interaction problems. For example, in this case, we have a two-span bridge, and we need to take into account what is happening at the base of this foundation. You can place this foundation in a soil pit, of course, but we didn't have one. But in this case, we can use a numerical model to represent the soil stiffness and behavior, and have the physical part in the lab. And because the connection between the mid-pier and the deck is monolithic, we needed to apply moments, so we had a couple of actuators applying displacements and moments at the top of the pier. Again, the case of the stiff coupling between the actuators is present because the actuators are in very close distance, so one influences the other, and in between them there is a very stiff stub at the top of the pier. Finally, again, along the lines of the distributed hybrid simulation test, I would like to present in anteprima a test we are planning for the next months, and this regards a timber structure. And this timber structure includes some shear walls, again from timber. And the idea of the test is the following. We will numerically represent the whole rest of the structure, except the lower part of the wall, which is going to be placed at the soil pit, at the University of Bristol. So at this soil pit, the actuators will be applying the vertical force, and the moment which is at that degree of freedom at the top of the first floor. And then the rest of the structure will be numerically represented at the Hanse University in Groningen. Also, this structure includes some damping devices, and these are some special type devices, sand dampers. The liquid inside the damper, the usual liquid inside the damper has been replaced by sand, and the internal plate has been replaced by a sphere. So actually the sphere plows in the sand, and with this it creates friction. And so it's not an independent device, but it's very cheap, it's very easy, it's very simple. If after some time the sand becomes pulverized, you can open up a tap, let it flow, and then fill it in again. And more on top of that, you can apply some pre-compression on this sand, so you can increase this friction at a measurable, in a measurable way. So you can apply strain gauges externally and measure that force, etc. So two of these dampers, one on the first floor and one on the third floor, will be represented in the University of Patras. All the other dampers will be numerically represented by in a numerical model. And then the whole coordination will be run at a computer at the University of Toronto. So this is going to happen next year. So, but I wanted to add another point to this whole thing, which is not exactly strictly linked to hybrid simulation, but it's linked to open science. We do all these tests, which cost enormously and take a lot of time, and we produce a large volume of test results. What do we do with them? We just keep in the drawer and wait for someone to ask for them, etc. Or how do we communicate, disseminate this data? This data has value. It's like an asset. And unlike other assets, the data, if you keep it in the drawer, does not deplete with time. It's still a full-scale test, and there are very few of them. Their value increases with demand. The more this data set is requested, the more its value. And also, the more it is shared, the higher becomes the value. So there is a loop there that the reusability of the data is very, very important and very useful for the progress. But to be reusable, this data should respect some principles, and this comes under the term FAIR, which stands for findable, accessible, interoperable, and reusable. So if you provide data, you should provide enough information about them. How did you measure? Where did you measure? What was the sensor? Which direction was the sensor? Any information that someone hasn't been present in the lab during the test can later on reproduce in his mind the whole test and have all the information to run numerical simulations. This is the maximum of the usefulness we can offer to users. And ultimately, the goal is that if the data is fair enough, it's mature enough with respect to fairness, then just a machine agent can locate the data, access the data, reuse the data, run a code or something, and at the same time maintaining the semantics of the initial test, because we have provided all the information, and also the producers of these data sets, of the original data sets. So it's very important. And within Project Iris, we have built a data portal, and there are similar other ones which advance, that we provide all this information of the metadata, and the data has to be stored somewhere in a credible and accessible repository like Zenodo and others, GitLab, GitHub, etc. So with this system, we try, and all this information has a DOI associated. So the information does not get lost over the time. It can be retrieved anytime in the future by any researcher. So it's a very important move, and actually I've noticed there is a work package also within ReLUIS trying to really advance in this direction. So regarding the hybrid simulation again, what is the picture? There is some research done advancing the method itself, not the applications. There are few industry-supported products that make it difficult for different labs to enter into the business of doing tests with this, and there are no standards of how to use the method. So still, you will notice that despite what I'm claiming of the experimental research, still resorts on basically quasi-static cyclic testing. But just hoping that the picture will change. Actually, I'm also citing two of the reports, one by FEMA and one that will appear in the next. It's in the group of the next Eurocodes, and it's about how to run, how to qualify the responsive structures through testing. So hybrid simulation is just, it's not just a tool, it's a way of solving problems. So it modifies itself, it's very flexible, that can fit the problem we need to solve. But we have to do some things about it, it's not automatic. It's not a method. And at the same time, it has considerable potential for earthquake engineering, but also for other disciplines. E con questo vorrei ringraziarvi per la vostra attenzione. Grazie.
Thank you, Stathis. I think, I don't know if there is any short question from you on the very interesting overview and presentation done by Stathis. Stathis, the ReLUIS was born when in the United States they were creating NIS. We always say this. And we know that NIS has been created just to create a network of the labs. We also know from American colleagues that the sustainability of such labs is not easy over time, as you said. And so, since many years, the Department of Civil Protection is not funding anymore the equipment to units. We are trying to really take advantage of the equipment present in different laboratories. And I agree with you, this is the future, because in order to have to perform very good testing, we need equipment, or we need people, advanced competencies. So it's not easy to buy just an actuator or shake table or a frame and then a reaction frame, and then you have a good lab. So this is the philosophy we are adopting. And I think Giampiero Lignola will present later a work package that is we are carrying out as ReLUIS in the last years. There is Felice Ponzo from University of Basilicata, Alberto Pavese, I think he was here yesterday from Pavia, and also University of Trento. The 4 funding labs try to guide the process in order to put online and together the data, as you said. Giampiero will tell you that it's not, as you know, an easy task, because each lab has its own system of data storage and management. But of course, the future is the one you said, and the fairness of this data is crucial. Otherwise, we make new papers, but we don't produce new knowledge. And but maybe I just tell you a last thing, so you can make a remark. My experience is that nowadays, if we talk about reinforced concrete, in many cases you showed that you are testing bare structures. I remember the SPEED project, it was a reference for many of us. Now we need also to study the issue of damage of structures. So in many cases we need to include also infills. For example, in Napoli we studied also the damage of reinforced plaster, which is in many cases something added to the structure. So I don't know which is your idea about the complexity that these tests take when you add infills, because it's very difficult to predict the dynamic properties, but also the damage degradation is more complex compared to bare structures. You have shown something, I think, for retrofit. You have already done something like that. What do you think about this?
So starting with your first remark about the labs and the cost, etc. So yeah, this is an investment for each lab. So, but especially regarding the hybrid simulation, the hardware regarding actuators, etc., it's not much different than a regular cyclic test. You don't need fast actuators, you don't need 3-stage servo valves, etc. The platforms for the hybrid simulation do exist, and they are very efficient. You need some experience. Everything comes down to the people finally. So this is a very important point. So for the investment, you just ask for funding once. But then to maintain the operation and the usefulness of such an infrastructure, a facility, the importance should be placed on people. So how do you maintain people within a lab? This is, excuse me, a very long story, and it depends on the country and the situation. Okay, so your second remark was about the infills. The infills. Regarding the infills, we have done quite a number of tests with infill frames. What happens is that the initial stages of the response, the response of the structure is pretty stiff because of the presence of infills. And provided that these infills are not built of concrete blocks, which makes this stiffness enormous, if they are regular bricks, then this stiffness decreases pretty fast at very small drifts. So we haven't encountered difficulties in the control for testing such structures. This way or the other, the infills are within the physical specimen. They are not in the model, so you don't have the issues of which model to use for the infills, which is a very debatable and very difficult thing to have because of difficulties in convergence of these models sometimes, etc. So as long as you don't go for very, very stiff structures like shear walls and things like that, you don't get into these problems. There are techniques to overcome, like the mixed mode, that you can have switching between displacements and force, but another tricks. But this is some part of the structures you can test. You can go into that direction when someone is experienced enough and can go into these resolving these problems. Okay.
Thank you.
Thank you very much.
Thank you, Stathis.